Thank you.
Okay, fine. So thank you, everybody. So I'm Jean-Luc from First Light Imaging. We're a company based in France. We are a camera manufacturer. We we are stemming from French public laboratories in astronomy, and we make cameras in the visible and in the infrared, mostly for adaptive optics in astronomy. We have recently been acquired by Andor and Oxford Instruments in Great Britain. And it turns out that a lot of people came to us and asked to turn our telescopes down and send them in space to observe the Earth and to detect greenhouse gas detection. Really, a lot of customers asked us, and we had to figure out what was the reason of that. So, just at the beginning, what is the greenhouse gas detection principle? So you have the sunlight, it goes through the atmosphere, and crossing the gas, it gets absorbed by different species of gases and makes a spectral signature into the light you get. You have on the right the spectrum you get from various species, and the game here is to be able to detect and disentangle several species, and in particular the water vapor molecule, which has a high absorbance signature. It is the light blue curve, and in between those windows, you are able to detect several gases. So historically, the CO2 detection was in the 5 microns, so in the mid-wave infrared region. But we are not manufacturing cameras in that wavelength, and we research why people are now turning to the shortwave infrared, which is in principle less favorable, but there is a lot of advantages by switching to this window. So once you have this principle in mind, how do you detect greenhouse gases from space? Then you put a slit spectrograph in a satellite. The ground is lighted by the sun, go through the atmosphere, get the spectral signature, and your slit is moving on the ground. And for each image you take, you have a bidimensional image where one direction is the slit, which is moving on the ground, and the other direction is the wavelength. So you have a multispectral image, or 1D. And by the displacement of the satellite on the ground, then you are able, by taking several images, to reconstruct a 3D image, X, Y, and wavelengths. And this has been demonstrated by the work of Al-Salam, and published. Here you have the reference of the publication. It's more or less what we call a push broom imager. And instead of having a moving mirror to reconstruct the image, we simply use the satellite displacement. So what to do with this 3D image? Then you have for each pixel a spectrum. And in this spectrum, you are able to find the gas signatures. And it turns out that the SWIR region is very interesting to be able to disentangle several species. You have here an example of spectrum you get for several pixels. So on the left, you have with different curves, the different pixels across one line of the slit. And you see that the signature of the gases are increasing when you get to from the black line to the red line. And on the right, you have the details of one spectrum and the gas signatures. And Al-Salem showed that it was interesting also to have a high resolution spectrum of your observation, to be able to disentangle the gas species and to be able to measure also the level of concentration. One point is why people are switching to shortwave infrared. That's because of the spatial resolution. So we have to come back to fundamental optics. So the angular resolution of an optical system is given by the diameter of the optics and the wavelengths. So it's proportional to the wavelengths and inversely proportional to the optics diameter. And if you observe at a very long distance, you see that you have to multiply by the distance, and you see that you need quite large optics if you want high resolution from space. So this is what is stated in the graph here. So I have plotted several cases of observation. And so on the right side, you have the resolution limit for a 25 centimeter optical system at low Earth orbit altitudes from 400 kilometers to 800 kilometers. And with respect to wavelengths, and as you are switching from short wave infrared, so around 1 microns, to long wave infrared, around 10 microns, you have a factor of 10, of course, in spatial resolution. So with 25 centimeter optics in shortwave infrared, you have a much more resolving capability than in mid-wave infrared or long-wave infrared. And on the right side, I've plotted the inverse problem. So given a resolution you want to obtain, so in this case 10 centimeter, what would be the telescope diameter with respect to the wavelength and the telescope altitude. And you see that if you are at a long wavelength, then to have a 10-meter resolution, which is the Copernicus resolution, so it is something that you should expect, then you need very, very large optics. Whereas in the SWIR domain, only small optics is sufficient. And this makes this compatible with CubeSats, whereas for longer wavelengths, you probably need a bigger satellite, which is more costly. And the advantage of CubeSats is that you can have plenty of them and have a revisit frequency, which is much higher than big satellites. Another point is the satellite speed. If you want to use a slit spectrograph, then the telescope is moving very fast when it is at low Earth orbit. And the resolution, the pixel resolution is given by the speed, the apparent speed of the slit on the ground. And if you want to have also a spatial resolution, then you have to take the images very fast. And you have here the curve of the theoretical spatial resolution you get with respect to the frame rates of your telescope. So it's almost independent on the altitude from 400 kilometers to 800 kilometers. There's not so much difference. It's around 6 to 7 kilometers per second. And then if you want a 10-meter resolution, then you may compute that you need 700 frames per second to be able to have this spatial resolution on the ground. You have here the curve of the spatial resolution with respect to the frame rate of the detector. So all those conclusions are that hyperspectral imaging is more favorable in the SWIR band for high spatial resolution. There is also some other advantages, like be able to disentangle more the gas species, but I'm not a specialist of that. The problem is that at long wavelengths, you need very large optics and costly that are not compatible with CubeSat and low-cost missions. And also, you need a high acquisition speed to get high spatial resolution that you may need for your detection. So if you come all those parameters together, we are the people that are able to produce such cameras, because it is the kind of technology we've developed for astronomy and for adaptive optics. And it turns out that we had to develop one of our camera for those space missions to adapt it for space use. This is what we call the C-RAD new space. So it's a short-range infrared camera that has sensitivity from 1 to 1.7 microns. And because it was designed for adaptive optics, it has also a very high acquisition frame rate, up to 600 frames per second. And this last point is decisive for people that want to integrate this kind of technology in CubeSat for LEO orbit observations. And this is what we can bring among several other advantages like low noise, low cost, and customization for a space mission. And well, that's it. And thank you for your attention.